The sheer scale of the cosmos has always captivated my imagination. Compared to some planetary bodies, our Earth appears as merely a tiny rocky fragment, and next to other stars, the Sun might seem like nothing more than a minuscule spark flickering in the vast icy emptiness. Today, we invite you on a thrilling journey to some of the most impressive cosmic objects known to humankind. Our extraordinary path begins with the magnificent Saturn, encircled by grand, unparalleled rings. We will fly over its raging, ever-changing atmosphere, weave our way through countless icy fragments, and encounter the mysterious Titan, one of its most intriguing moons. After that, we will traverse hundreds of light-years in mere moments to witness a ring system tens of times larger, known as Super Saturn. Next, we anticipate an encounter with the unpredictable and potentially dangerous Betelgeuse, a dying star that could explode into an all-consuming supernova at any moment, lighting up the cosmos. Leaving it behind, we will head towards the majestic red hypergiant Stephenson 2-18, one of the largest stars known in our galaxy. Following that, we will visit another dying giant, belonging to a rare and unique class of carbon stars. Beyond the Milky Way, we'll journey to the astonishing and enigmatic Andromeda, our closest galaxy. After exploring its sparkling stellar arms and impenetrable nebulae, we will continue our voyage to one of the most expansive voids in the universe, whose origin is still shrouded in deep mystery. Prepare yourselves, our journey begins now. Saturn's rings lack a sharply defined, fixed boundary. Their observable extent is around 280,000 kilometers. However, beyond these limits lie the finest clusters of dust and rarefied gas. The diameter of these structures, by some estimates, reaches 16 million kilometers, but they cannot be discerned from Earth due to their extremely low density, making them virtually invisible to our telescopes. Despite their impressive size, the total mass of the entire ring system is very small by cosmic standards, estimated at 3 × 10⁻¹9 kilograms, which is roughly 2,000 times less than the Moon's mass. Solid objects, such as ice chunks and rocks, account for only about 3% of the structure's total volume. The rest is filled with rarefied gas and cosmic dust, creating this majestic yet ethereal system. The disk surrounding Saturn is conventionally divided into several large, distinct rings. However, with a sufficiently powerful optical telescope, it is easy to see that each consists of numerous thin, delicate circles separated by narrow gaps. These gaps arise due to the gravitational influence of both the planet itself and its many moons, whose attraction shapes these spaces. Some of these gaps extend for hundreds of kilometers. Although Saturn's disk reflects several times more sunlight than the gas giant itself, some rings are almost impossible to see. For example, the D ring, closest to the planet, is composed of tiny crystals of water ice and frozen methane. Its upper limit is generally considered to be 165,000 kilometers from the planet's hypothetical surface. In its inner part, the ring has no clear boundary and gradually and smoothly transitions into Saturn's atmosphere, dissolving into it. This is followed by the much brighter and more massive C ring, approximately 17,500 kilometers wide. It is composed of cosmic bodies up to 2 meters in size, which collectively account for only 0.3% of the disk's total mass. The brightest and most prominent part of the disk is located further out and is designated the B ring. It begins roughly 34,000 kilometers from the gas giant's surface, and this region spans 25,000 kilometers in width. The thickness of most of the ring does not exceed 5 to 10 meters. However, its outer part forms a vertical edge up to 2.5 kilometers high, giving it a distinctive appearance. The outermost visible ring of Saturn begins 64,000 kilometers from the planet's surface. Its width is about 14,600 kilometers. Within it are not only relatively large ice fragments over 10 meters in size, but also some moons, such as Pan, Daphnis, and others. The existence of such large objects may support the theory that the rings formed from a shattered icy moon. However, they could also have formed later through the collision and accretion of smaller fragments, which is another version of their origin. Beyond this central part of the disk, which constitutes the main ring formation, lie the almost invisible F, G, and E rings. These are formed from cosmic dust and extremely rarefied gas. Indeed, most of Saturn's large moons actively interact with its intricate ring system. If we mentally transport ourselves 179,000 kilometers into the region of the so-called E-ring, we can find a unique celestial body known as Enceladus. With a modest diameter of only 500 kilometers, it is certainly not among the largest moons of the gas giant, but it attracts the close attention of researchers for a variety of other, very significant reasons. The fact is that Enceladus is one of the few cosmic objects within our solar system that exhibits clear and highly active cryovolcanic activity. Careful analysis of observed emissions emanating from its interior convincingly indicates that a vast ocean of liquid water is hidden beneath its massive icy surface. Mathematical modeling of this subsurface body of water shows that its temperature ranges from -45 degrees Celsius in the upper layers to 0 degrees Celsius in the bottom region. Thanks to a significant content of dissolved salts and ammonia, the ocean does not freeze even at negative temperatures, and a dense ice crust, approximately 2 kilometers thick, reliably covers and effectively insulates it. The temperature on the outer surface of this celestial body is approximately 75 Kelvin, equivalent to -198 degrees Celsius. At the same time, its atmospheric shell is extremely tenuous and consists of 91% water vapor. In addition, it contains components such as nitrogen, carbon dioxide, and methane. Powerful geysers, periodically erupting from numerous cracks in the moon's icy crust, continuously replenish its gaseous envelope. However, the moon's gravitational pull is insufficient to reliably retain this gas. The upper layers of its atmosphere constantly lose particles, which in turn replenish the material of the E-ring. At the same time, Enceladus continuously captures matter from the surrounding cosmic space, thus maintaining a unique dynamic balance. It is known that the geyser activity of this celestial body directly depends on its orbital motion around Saturn. Powerful tidal forces from the gas giant likely deform the moon's icy crust, leading to the formation of numerous cracks and provoking eruptions. When Enceladus moves to its maximum distance from the gas giant, the fissures are gradually covered by a fresh ice crust. It has also been established that cryogeyser emissions contain complex organic molecules, which means that conditions in the subsurface ocean could hypothetically be quite suitable for the origin and development of biological life. Noticeably further, at a distance of approximately 300,000 kilometers from the gas giant, lies its fifth largest and most massive moon, named Tethys. It is notable for sharing its orbit with two other cosmic objects, Telesto and Calypso. These small bodies are located at the so-called stable Lagrange points. Telesto precedes the main moon in its orbital motion by 60 degrees, while Calypso, conversely, lags behind by the same angular measure. Unlike the massive and almost perfectly spherical Tethys, these two celestial bodies, Telesto and Calypso, are small in size and possess an irregular asymmetrical shape. Their transverse dimensions range from 20 to 30 kilometers, and their total mass is only a few trillion tons. Mathematical modeling convincingly shows that Calypso and Telesto could not have originally formed in the same orbit as the much more massive body, meaning they occupied their current positions significantly later. Tethys itself is a celestial body with a diameter of about 1,060 kilometers, composed mainly of water ice with a small but noticeable admixture of rocky materials. The most remarkable part of its relief is a gigantic impact crater named Odysseus. Its diameter is about 450 kilometers, which is approximately half the diameter of Tethys itself, and its depth reaches 3 kilometers. Also on the surface of this moon, one can easily notice an incredibly large fissure known as Ithaca Chasma. Its length is around 2,000 kilometers, which is approximately 1/3 of the celestial body's circumference, and its width reaches 100 kilometers. The depth of this grand rift varies between 3 and 5,000 meters, and its floor is riddled with numerous craters and small irregularities. According to one of the most widespread theories, Ithaca Chasma formed as a result of the gradual freezing of Tethys' internal ocean. As water transformed into ice, it expanded in volume, leading to the cracking and rupture of the moon's outer crust. Another hypothesis links the appearance of this colossal rift to the Odysseus impact crater. It is presumed that powerful shock waves from the cosmic collision traversed all of Tethys, creating a strong resonance around its circumference. As a result of these processes, the cosmic object's crust was shattered, giving rise to an incredibly large fissure. Even further from Saturn lies its largest moon, named Titan, which, like a precious gem, displays a plethora of extraordinary characteristics. With an impressive diameter of 5,152 kilometers, it rightfully holds the second place among the moons of our solar system in terms of its size, surpassed only by Ganymede. It is also a notable fact that Titan is 5.5% larger than even the planet Mercury. Moreover, it is the only moon in the entire solar system that can boast a dense atmosphere and visible accumulations of liquid substances on its surface. Due to its significant distance from the Sun, the temperature regime of this celestial body is quite harsh, measuring only about 94 Kelvin, which is equivalent to -180 degrees Celsius. Despite its relatively modest mass, Titan is able to retain an atmosphere that is 1.5 times denser than Earth's. Over 98% of its composition is nitrogen. In addition, the gaseous envelope also contains methane and a number of other gases. Under the relentless influence of the solar wind, nitrogen and various hydrocarbon compounds in the upper atmosphere undergo transformations, turning into more complex organic substances, which then slowly descend, gradually settling on the surface. It is because of this opaque hydrocarbon smog that observing the moon's surface in the optical range becomes impossible. The most reliable existing models of Titan's internal structure place a massive rocky core in its central part, with a diameter of approximately 3,400 kilometers. This core is surrounded by a substantial layer of superdense ice, which, in turn, forms the floor for a cool, salty ocean containing up to 10% dissolved ammonia. Above this ocean, a multi-kilometer crust of water ice mixed with methane hydrate is spread. At such extremely low temperatures, ice behaves like a complete solid, forming mountain ranges and highlands on the surface. At the same time, lowlands and numerous fissures are filled with lakes composed of liquid ethane and other hydrocarbons. The solar wind and Saturn's powerful magnetic field continuously deplete Titan's atmosphere. However, the moon's internal processes constantly replenish the gaseous envelope, allowing this process to continue for billions of years. When the Sun, in the distant future, transforms into a red giant, it will be able to evaporate the hydrocarbon haze and melt Titan's eternal ice. After that, the Moon may become a significantly more accessible and potentially habitable place for life to originate. However, this grand event is still a very long way off. At a distance of 4 astronomical units from a young Sun-like star, located 434 light-years from Earth, lies a truly astonishing object, unofficially named Super Saturn. It is a brown dwarf or a massive gas giant with a mass of about 20 times that of Jupiter. Observations show that this is a young planet, estimated to be about 15 to 16 million years old, and it is still in the process of formation. Most of its atmosphere consists of hydrogen and helium, and inside lies a massive metallic core. This enigmatic object is surrounded by a ring system reminiscent of Saturn's, but far more impressive in size. Transit observations revealed at least 37 distinctly defined rings, with the outer radius of the largest one reaching approximately 0.6 astronomical units. This magnitude is comparable to the size of Venus's orbit and is about 640 times greater than the radius of Saturn's rings. According to calculations, the total mass of the circumplanetary disk exceeds that of Earth, and its behavior shows signs of chaos. Mathematical modeling convincingly demonstrates that such structures are not stable and gradually disintegrate over time. Some of their constituent objects lose speed and fall onto the central planet, while others, conversely, gain acceleration and permanently leave the disk. However, this process is significantly stretched out over time and can last for several 100 million years. A large gap was also observed in the ring system, with a radius of approximately 0.4 astronomical units. This gap is considered indirect evidence for the existence of an exomoon in this region, with a mass approaching 80% of Earth's. According to modern understanding of cosmic body physics, such an object is capable of clearing its orbit of small debris, forming a wide gap in the ring-like structure. In addition, observations indicate the presence of at least two more celestial bodies, each with a mass of about 30% of Earth's, located at a distance of approximately 0.25 astronomical units from the center of the brown dwarf. By analogy with the large planets we know, it is logical to assume that several hundred exomoons, possibly including very massive bodies, could be located within the gravitational influence of the central object. Modeling such a system, taking into account radiation from the parent star, the heat flow from the giant planet, and tidal effects, shows that the temperature of these celestial bodies could approach values quite comfortable for potential life. One can only imagine how spectacular and breathtaking the night sky would appear from the surface of such an exomoon, where cosmic phenomena are presented on an entirely different scale. At such a significant distance, the brown dwarf would occupy an area in the sky 70 times larger than that of the full moon. Its soft, diffuse glow could dispel utter darkness, transforming night into something akin to hazy, ghostly twilight. Instead of the familiar scattering of stars, the exoplanet's skies would be traversed from horizon to horizon by enormous, luminous bands, creating a truly unique visual spectacle. At the same time, it is worth noting that powerful tidal forces emanating from the nearby massive body could provoke numerous eruptions on the moon's surface, and its hypothetical ocean could engulf the land with gigantic, destructive waves. The width of the tidal zone under such extreme conditions could reach hundreds of kilometers, allowing it to be considered a unique climatic zone, representing something between land and the ocean floor, with its specific flora and fauna. Nevertheless, it is extremely important to remember that such structures are generally unstable and can change their appearance dramatically and quickly beyond recognition. Currently, it is exceedingly difficult to say with certainty how long humanity will be able to admire these giant rings, and what they will transform into after millions of years of cosmic evolution. The end of 2019 was marked for astronomical observatories by an alarming report of a sharp decrease in the brightness of the star known as Betelgeuse. According to careful observations, its luminosity rapidly dropped to 36% of its standard, usual level within a couple of months. Some scientists, based on this data, began predicting an imminent supernova explosion, which, if it occurred, could become the brightest object in the night sky in recorded history. There is also a serious hypothesis that a powerful stream of gamma radiation from such an explosion could pose a potential, extremely serious threat to life on our planet, capable of causing mass extinctions. In April 2020, astronomers confidently stated that Betelgeuse had fully restored its luminosity to standard, normal levels. Although it could still theoretically explode at any moment, predicting this grand event with absolute certainty remains impossible. Various hypotheses are actively being put forward regarding the causes of the star's anomalous dimming. The leading and most convincing hypothesis is the idea of a giant cloud of gas and dust that Betelgeuse recently ejected towards the Sun, creating a temporary eclipse effect. June 2021 brought definitive confirmation of this conjecture, thanks to data obtained from ground-based telescopes. Astronomers continue to closely observe the object, while astrophysicists actively model the complex processes occurring within its interior. Before we attempt to deeply understand the phenomenon that occurred, it is worth gaining a clear understanding of what Betelgeuse itself represents. This remarkable object is classified as a red supergiant, and according to modern stellar evolution theory, is in the final stage of its life cycle. Its luminosity and radius are constantly changing, exhibiting significant fluctuations, and the star's outer layers are extremely unstable. Periodically, this majestic luminary ejects millions of tons of superheated gas into boundless cosmic space, forming gigantic prominences. Gradually cooling, these replenish the vast gaseous nebula that surrounds Betelgeuse, creating a majestic halo around it. The mass of this star is about 17 solar masses, and its diameter is only approximately determined, ranging from 700 to 880 times the Sun's diameter. If Betelgeuse were hypothetically placed at the center of our solar system, it would easily engulf all planets up to and including Mars, as well as a significant portion of the asteroid belt, demonstrating its colossal size. It is important to note that the star does not have a clearly defined edge, as its outer envelopes are extremely rarefied and diffuse. Furthermore, the object is surrounded by a gigantic gaseous nebula, consisting of solidified prominences and tiny particles of stellar wind. Remarkably, the density of stellar matter at the star's hypothetical boundaries only slightly exceeds the density of the nebula itself, making its contours blurry and transient. Betelgeuse is an extremely bright star. Its minimum luminosity is 90,000 times that of the Sun, and at its peak brightness, the object radiates 150,000 times more light energy than the Sun, astounding with its splendor. However, its temperature is not very high, ranging from 3,400 to 3,800 Kelvin, which corresponds to the red part of the electromagnetic spectrum. In the star's unstable outer layers, unpredictable and extremely complex processes constantly occur, changing the object's luminosity in a very erratic manner. Its main pulsation period is approximately 420 days. However, less distinct cycles, both longer and shorter, can also be identified, adding complexity to its study. In addition, completely unpredictable flares and dimmings of the star are observed from time to time, posing new mysteries for astronomers. Due to such variability and inconstancy, determining the exact distance to this cosmic object is quite difficult. According to measurements successfully carried out by the Gaia satellite in 2020, the distance from our solar system to Betelgeuse ranges from 500 to 650 light-years. In accordance with current scientific understanding of stellar evolution stages, Betelgeuse formed approximately 8.5 million years ago. The initial mass of this star did not exceed 20 solar masses. Its life began in a vast cloud of interstellar gas and dust, which gradually compressed and heated under the influence of gravitational forces. This is how a protostar, the progenitor of modern Betelgeuse, came into being. At a certain point, the temperature and pressure in its central part reached critical values, initiating a chain reaction of thermonuclear fusion, where hydrogen was converted into helium. Soon after, thermonuclear interaction encompassed the entire cosmic object, and a new, bright star shone in the boundless night sky. Thus begins the longest and most stable period in the life of any celestial body, the main sequence stage. Throughout this stage, the primary energy source for the star is the process of hydrogen atomic nuclei fusing to form helium. Notably, the more massive a star, the faster this process occurs. The lifespan of giant stars, such as Betelgeuse, is measured in mere millions of years, while less massive red dwarfs can emit light for billions of years. In any case, a celestial body spends approximately 90% of its total life in the main sequence stage. As it accumulates, helium gradually sinks to the center of the object, where it forms a dense helium core. The further fate of a star is almost entirely determined by its initial mass. For example, celestial objects whose mass does not exceed 20% of the Sun's do not end their life cycle with a grand explosion, unlike much more massive stellar systems. Having gradually processed almost all of their hydrogen supply, they slowly transform into blue dwarfs, hot and relatively compact astronomical objects. However, the minimum time interval required for such a metamorphosis is about 1 trillion years, which is 72 times greater than the estimated age of our universe. Consequently, the chances of discovering a blue dwarf currently are practically non-existent. After the complete exhaustion of hydrogen reserves, thermonuclear reactions within such an object will cease, and it will transform into a white dwarf, which will consist of 99% helium. It awaits trillions of years of gradual fading and cooling until only a barely warm and virtually invisible black dwarf remains where a bright star once shone. In the case that the mass of a cosmic object is between 0.2 and 8 solar masses, its evolutionary development proceeds along a significantly more complex and multi-stage path. Helium, formed during thermonuclear burning, continuously replenishes the star's core, and gravitational forces increasingly compress and heat its central part. At a certain point, a new reaction of helium nuclei fusion begins, leading to the formation of carbon. The star begins to expand rapidly. Its radius significantly increases, while the temperature of its outer layers, conversely, noticeably decreases. In this scenario, the object transforms into a red giant or subgiant. Relatively light celestial bodies, whose mass does not exceed 50% of the Sun's, are unable to maintain the conditions necessary for a stable, sustained helium-carbon reaction within themselves. In them, such transformations occur only sporadically from time to time. In more massive objects, reactions in the stellar core can continue further, forming carbon, oxygen, and heavier chemical elements up to nickel and iron. Ultimately, the star sheds its outer envelopes, leaving behind a white dwarf surrounded by a picturesque planetary nebula. If the mass of the original star did not exceed half a solar mass, the white dwarf would primarily consist of helium with a small admixture of heavier elements. Otherwise, most of the white dwarf would be composed of oxygen and carbon. And with a sufficiently massive progenitor star, neon, magnesium, and even iron could also be found in its composition. The evolution of particularly massive cosmic objects has its unique features. As the heavier a star, the more massive its core becomes. If the star's mass exceeds 8 or more solar masses, its core can overcome the so-called Chandrasekhar limit, which is approximately 1.4 solar masses. In this critical case, the forces of internal electromagnetic repulsion are no longer sufficient to fully compensate for powerful gravitational compression. Within mere moments, lasting only seconds, the massive stellar core rapidly shrinks in size, pulling all its surrounding outer gaseous envelopes with it. This colossal, explosive compression leads to extreme heating of the inner core, raising its temperature to hundreds of millions of Kelvin. Under the influence of this monstrous pressure, electrons are literally forced into atomic nuclei, transforming some of them into neutrons and generating an enormous amount of neutrinos. However, even such dense matter cannot contain these most elusive particles in the entire universe. Thus, within a few seconds, neutrinos escape the collapsing star, carrying away a significant portion of its thermal energy. As a result of these processes, the star begins to experience incredible internal pressure, as densely compressed protons begin to repel each other with colossal force. In response, the core begins to expand rapidly, at the same speed it compressed just seconds earlier, generating a powerful shock wave in the surrounding matter. This results in an explosion of unimaginable power, capable of scattering the star's outer layers over a grand distance. In this inferno, thermonuclear reactions become possible that cannot be reproduced anywhere else in the universe. This is how heavy chemical elements such as gold, lead, or uranium are born. The nebula formed after the explosion gradually cools and fragments into individual gas and dust clouds, which then recompress under the influence of gravity and transform into new stars and planetary systems. In place of the deceased star remains a tiny but extremely dense and heavy object, commonly called a neutron star. However, if the initial mass of the star exceeded 18 to 20 solar masses, its core after the grand explosion would collapse into a black hole, a mysterious and enigmatic object that distorts space and time around itself. Mathematical modeling and theoretical calculations show that particularly large stars, whose mass exceeds 100 solar masses, could hypothetically be completely destroyed by an explosion. In this scenario, all their matter would be scattered by the shockwave for many light years around, or it would completely transform into powerful electromagnetic radiation. The electromagnetic pulse that accompanies a supernova explosion can travel hundreds of light years. Initially, the radiation is incredibly powerful and theoretically capable of destroying all life in its path. However, with increasing distance, the density of the energy flux decreases exponentially, and the deadly rays gradually dissipate into boundless cosmic space. Calculations show that a star like Betelgeuse could pose a threat within a radius of up to 100 light-years. It is impossible to predict the exact moment when this star will explode as a supernova. However, it is most likely to occur within the next 100,000 years. According to calculations, Betelgeuse's explosion could be as bright as the full moon. For a period, the dying star will be the dominant object in Earth's night sky, and then it will gradually fade. The object will no longer be observable with the naked eye. Only the most powerful telescopes will be able to detect the radiation of a tiny neutron star. If Betelgeuse's mass is actually greater than commonly believed, a black hole could form after its explosion. In this case, the energy burst would be much smaller, and the spectacle far less grand for Earth observers. In any case, planet Earth is not in danger. Betelgeuse is too far from the solar system, and the gamma-ray burst accompanying a supernova explosion will not be able to harm our planet. The matter ejected by the explosion will only reach the vicinity of our system in 6 million years. Its speed, according to calculations, will be about 13 kilometers per second and will be easily extinguished by the solar wind, without reaching the inner part of the system. For a long time, the largest star known to humanity was UY Scuti, located 9,500 light-years from the Sun. This star is so enormous that if hypothetically placed at the center of the solar system, it would engulf Jupiter's orbit. Its radius can reach 1,900 solar radii, and its volume can exceed 5 billion solar volumes. However, recently, a new cosmic giant has laid claim to the title of the largest star in the observed universe. It is known as Stephenson 218, Stephenson 218, or RSGC 218. This star is located approximately 20,000 light-years from the Sun and is part of the Stephenson Open Star Cluster. However, some astronomers believe that classifying this cosmic object as part of the Stephenson cluster is not entirely accurate. Be that as it may, Stephenson 218 is located in the constellation Scutum and retains its traditionally received name. The celestial body itself was catalogued in the stellar sky back in the 1990s, but colossal accumulations of cosmic dust hinder observations of star clusters in the constellation Scutum, hiding them from curious eyes. For this reason, it was only in 2020 that scientists managed to obtain data on its true size, and these findings were truly astonishing. According to some calculations, the radius of Stephenson 218 could potentially reach a staggering 15 billion kilometers, which is 10 times the distance from Earth to the Sun, and 2,150 times the radius of our star. This means that the volume of this hypergiant surpasses the Sun's by approximately 10 billion times. If Stephenson 218 were placed in the central part of the solar system, it would engulf Saturn along with its rings and moons, not to mention the inner planets. For light to complete one full revolution around this giant star along its equator, it would take almost 8.5 hours. Within the same time frame, light from the Sun reaches Pluto at the most distant point of its orbit. The luminosity of this giant, according to calculations, can reach 440,000 times that of the Sun. However, its surface temperature is not as high, measuring around 3,200 Kelvin. This is almost half that of the Sun and corresponds to the red region of the light spectrum. That is why Stephenson 2-18 is classified as a red supergiant. Furthermore, such a low temperature indicates that most of the star's radiation falls within the visible and thermal spectrum, while the proportion of life-damaging ultraviolet and X-ray radiation is relatively small. Nevertheless, despite its colossal size and incredible luminosity, Stephenson 2-18 is not visible from Earth with the naked eye. This circumstance is due to both its low surface temperature and the dense clouds of cosmic dust and gas that effectively conceal the giant star from Earth observers. These clouds absorb and scatter the light emanating from the star, significantly hindering its detailed study. The mass of Stephenson 2-18 is currently unknown, but if we assume its internal structure is similar to UY Scuti and other supergiants, then the mass of this star should be within 20 solar masses. In such a case, the average density of such supergiants should be incredibly low and approximately correspond to the density of Earth's atmosphere at an altitude of about 90 kilometers above sea level, practically at the edge of space. It is astonishing how thermonuclear reactions are sustained under such conditions, allowing these stars to emit light. The sizes of supergiants are so immense that these stars barely maintain stability. Most of them exhibit variability in their luminosity, and this variability is typically unpredictable. This is not surprising, as the absolute majority of supergiants are in the final stage of their life cycle and could transform into a supernova literally at any moment. According to modern scientific understanding of stellar evolution, red hypergiants are stars with an initial mass of 10 to 40 solar masses. Thermonuclear reactions in their interiors rapidly burn hydrogen, transforming it into helium. Subsequently, the primary energy source for the star becomes the fusion reactions of helium, carbon, oxygen, and lithium. The lifespan of stars of this type is very short, only a few million years. The hypergiant stage is the final one in their life cycle. During their development, future supergiants rapidly increase in volume and lose mass due to intense stellar wind. Clouds of cosmic dust and gas adjacent to the original star are rapidly absorbed by the rapidly expanding star. However, its own stellar wind forms a new nebula around the star. The star's lifetime is insufficient for planets to form within this nebula. Ultimately, the hypergiant explodes, forming a supernova or even a hypernova. Its outer envelopes disperse and gradually cool, transforming into a nebula. And the core becomes a neutron star or a black hole, depending on its mass. A hypernova explosion is accompanied by a colossal release of hard X-ray radiation, capable of destroying all forms of life within several light-years. Fortunately for our planet, all hypergiants known to humanity are located significantly further away. Due to the intense emission of charged particles, stars of this type gradually slow their rotation, and their outer envelopes eventually almost completely stop. Meanwhile, the central core of the star continues to rotate, and the difference in rotation speeds between the core and the outer layers can reach very significant values. Thanks to its exceptional luminosity, relatively low surface temperature, and enormous size, Stephenson 2-18 should possess a truly gigantic habitable zone. Its central part, according to calculations, should be located at a distance of approximately 663 astronomical units from the star's center, which is about 20 times the orbit of Pluto. The area of this habitable zone, in turn, should be more than 1 billion times larger than the Sun's. Scientists do not rule out the possibility of planetary systems existing near hypergiants. However, the relatively short lifespan of these stars and their internal instability make such a scenario highly unlikely. In any case, no confirmed exoplanet has been discovered in the vicinity of a supergiant to date. Stephenson 2-18 is so far away that light from it reaches Earth after 20,000 years. It is quite possible that at this very moment its core is collapsing, transforming into a super-dense neutron star, while its superheated outer envelopes are rapidly dispersing into the silent cosmos surrounding the giant star. Nevertheless, humanity will only learn about this grand event in the distant future. At a distance of 650 light-years from Earth lies a majestic cosmic body known as IRC plus 10216, or CW Leonis. At its maximum pulsation phase, its radius can reach 560 solar radii, which is approximately 2.6 times the distance from our planet to the Sun. If CW Leonis were hypothetically placed at the center of our solar system, its surface would engulf all planets up to Mars and reach the inner boundary of the asteroid belt. However, the star's mass is relatively small, ranging from 1.5 to 4 solar masses. Its surface temperature is only 2,300 Kelvin, or approximately 2,000 degrees Celsius. Nevertheless, due to its incredible size, the star emits, on average, 8,500 times more energy than our Sun. Like all red giants, CW Leonis is in the final stage of its evolutionary path. Its exact age has not yet been determined, but it is known to be several billion years old. It is presumed that, in its early existence, the star was a blue-white star with a mass of 3 to 5 solar masses. However, about 1 billion years ago, a significant portion of the hydrogen in CW Leonis burned out, converting into helium. Gradually sinking to the center of the star, helium displaced the remaining hydrogen, forming a superheated core that no longer participates in thermonuclear reactions. This process is characteristic of all stars with masses close to the Sun's, and serves as the starting point for their subsequent transformation into red giants. The star's internal pressure leads to its significant increase in size, as a result of which the star's outer envelopes become more rarefied and unstable. The diameter of the cosmic object increases tenfold, and its color gradually changes to a deep blood red. Nevertheless, thermonuclear reactions continue deep within the star, causing the pressure and temperature of the stellar plasma to continue to rise. At a certain point, a chain reaction of helium nuclei fusion begins, leading to the formation of carbon, known as the helium flash. This is a complex, multi-level physical process that fundamentally alters the star's internal structure. Its core becomes incredibly hot, while its outer envelopes, conversely, cool and darken. Currently, CW Leonis contains a colossal amount of carbon. However, its mass is insufficient to transition to the next level of nuclear fusion. Ultimately, the thermonuclear fire within the object becomes unstable. When the star gradually fades due to insufficient fuel and decreasing temperature, its stellar matter begins to slowly cool and contract under the influence of its own gravitational attraction. As a result, the star's internal regions heat up again, and the nuclear reaction ignites with renewed, increasing force. Having received an additional portion of thermal energy, the stellar matter expands again, which leads to the interruption of the burning process. It is presumed that this cyclic mechanism underlies the periodic changes in the star's brightness. CW Leonis exhibits pulsations with a period of 649 days, reaching a maximum luminosity that is 11,300 times that of the Sun. At the same time, at the lowest point of its cycle, the object emits 6,250 times more energy than our Sun. At the moment of contraction, the upper layers of stellar matter partially separate from the star, thereby replenishing the vast carbon-oxygen gaseous nebula surrounding this giant. According to calculations, this process leads to CW Leonis losing 4 times 10 to the 20th tons of matter annually, which is approximately 7 times the mass of planet Earth. Observations indicate that the age of the circumstellar nebula is at least 69,000 years. Its total mass is estimated at approximately 1.5 solar masses, and its size reaches 84,000 astronomical units. The nebula has a complex internal structure, which includes thickenings and concentrations of gaseous matter, as well as arcs and irregular ring-shaped formations. It is believed that the cause of such complexity is magnetic activity and stellar wind, generated by the unstable nearby star. The chemical composition of the gas cloud enveloping CW Leonis is of significant research interest. Data obtained from spectral analysis show that it contains about 70 different chemical compounds. For example, carbon dioxide, water, and ammonia. In addition, the nebula includes many elements located in the upper part of the periodic table, up to iron. It is quite probable that in the distant past, CW Leonis had planets. However, they were apparently engulfed by the star during its expansion phase. In any case, many years of observations have not revealed any clear signs of their existence. However, back in 1994, barely discernible distortions in the star's orbit were recorded. And in 2017, mysterious shifts in matter within the gas and dust clouds surrounding the star were discovered. The cause of these phenomena could be a small red dwarf orbiting the giant. Nevertheless, its radiation has not yet been detected. The reason for this phenomenon could be a nearby nebula that scatters and re-emits the energy flux from closely located light sources. This phenomenon effectively masks any nearby objects, preventing them from being properly observed. It is assumed that the mass of CW Leonis's hypothetical stellar companion is certainly less than the Sun's, and it takes approximately 100 years to complete a full orbit around the giant. Another notable fact is the relatively high concentration of water in the vicinity and outer envelopes of the star. Initially, it was assumed that the expanding star melted and engulfed icy comets. However, observations conducted in 2009 demonstrated that the temperature of some spectral lines reaches 1000 Kelvin, which is only possible if water vapor forms directly in the outer layers of the giant. This fact did not align with the then-accepted model of red giant structure. According to it, all oxygen contained in the stellar matter and necessary for water synthesis should have been completely consumed in the formation of carbon monoxide. To explain this discrepancy, a new hypothesis was proposed. According to it, molecules of silicon and carbon oxides are destroyed by powerful ultraviolet radiation. After this, the liberated oxygen reacts with hydrogen, forming superheated water vapor. The weak point of this assumption remains the question of the source of ultraviolet radiation. Such reactions can only occur at a sufficiently high temperature, i.e., within the stellar matter. However, stellar matter practically does not transmit cosmic rays. This paradox can be resolved by assuming that due to the star's instability, large ruptures and regions of reduced density periodically arise on its surface, which are more open to the penetration of ultraviolet light. The total mass of water vapor present in the atmosphere and outer envelopes of this star is estimated at several quintillion tons. This astonishing figure may seem colossal. However, when viewed in perspective, water actually constitutes only 1/billionth of the entire mass of this celestial body. According to current understanding regarding the evolution of stellar objects, CW Leonis is experiencing its final moments as a red giant. Over the next 10,000 to 30,000 years, it will finally exhaust its stellar fuel reserves, after which its outer envelopes will be shed in a powerful explosion. In place of this star will remain an incredibly hot and extremely dense cosmic object known as a white dwarf. Its mass will be approximately 80% of the Sun's, and its temperature in the first moments after formation will reach several million degrees. Nevertheless, deprived of an internal energy source, it is doomed to billions of years of slow but relentless fading. Ultimately, this celestial body will become virtually invisible against the backdrop of the boundless cosmic void, transforming into a mysterious black dwarf. However, this event will happen a very, very long time from now. The shockwave and extreme temperature prevailing at the epicenter of the explosion will produce new chemical elements that cannot be obtained in the depths of stars. Among them, for example, uranium, gold, and lead. Subsequently, these elements will become an integral part of new celestial bodies. Millions of years later, radioactive decay will warm the interiors of planets, melt ice, and enrich oceans with trace elements, thereby creating favorable conditions for the emergence of life. The universe is in a state of continuous evolution, and this process is inconceivable without global cataclysms and destructions. But ultimately, after every storm, a new dawn invariably follows. 1885. Earth. The attention of all astronomers on the planet is drawn to an astonishing astronomical phenomenon. A brilliant flash, occurring in the region of the Andromeda Nebula, briefly outshines nearby stars. This striking supernova is named S Andromedae, and its anomalous parameters baffle astronomers for a long time. But just 6 months later, the star rapidly dims and soon disappears from the sky forever. Unfortunately, at the time of the outburst, generally accepted notions about the structure of the universe were very far from modern ones. In those days, astronomers did not yet possess the ability to measure distances to cosmic bodies. So the bright spot in the constellation Andromeda, also known as Object M31, was considered an ordinary reflective nebula located on the outskirts of the Milky Way. Meanwhile, the advent of new, more powerful telescopes and progress in space technology gradually changed the situation. As early as the 1920s, observations made by Edwin Hubble and other astronomers convincingly proved that the Andromeda Nebula was another galaxy, much like the Milky Way. A century has passed since then, and during this time, science has advanced significantly. Currently, it is known that the Andromeda Galaxy has a spiral structure and contains approximately 1 trillion stars. Its diameter exceeds 150,000 light-years, and its mass is relatively modest, ranging from 800 billion to 1.5 trillion solar masses, roughly corresponding to the mass of the Milky Way. This is believed to be due to an abundance of red dwarfs and a lower content of dark matter in its composition. As with all spiral galaxies, Andromeda's center hosts a massive nucleus consisting of millions of densely packed stars. Its brilliance is so great that it overwhelms observational instruments, preventing individual stars from being distinguished. For this reason, the remnants of the 1885 supernova, known as S Andromedae, could not be detected for a long time, even though preserved records clearly indicated that it exploded near the galaxy's center. It was only in 1988, 103 years after the legendary outburst, that a small nebula was discovered a short distance from the nucleus, a dark spot standing out against the dazzling central region. Through spectral analysis and modeling of its proper motion, it was reliably established that it is a remnant of S Andromedae. Thus, this cosmic object became the first supernova discovered outside the Milky Way. Carefully studying the central part of Andromeda, one can easily notice its unique difference from other spiral galaxies. It presents an unusual double nucleus, whose origin is not yet fully understood. The brighter and more extensive part is located slightly off the galaxy's geometric center, and is a gigantic supercluster of many bright stars with a total size of about 7 light-years. The second part is closer to the center, yet noticeably dimmer and smaller. Its diameter is approximately 1.3 light-years. It is hypothesized that this region conceals a supermassive black hole, approximately 50 million times heavier than the Sun. The nature of such a strange phenomenon remains a subject of scientific debate. According to some hypotheses, in the distant past, M31 absorbed and dispersed a fairly large satellite galaxy, and the bright region is the remnant of its nucleus. Other hypotheses suggest that Andromeda's center does indeed have a single structure, but it is divided by a band of opaque dust, creating an unusual optical effect. Due to the galaxy's distance and inconvenient spatial orientation, it is currently impossible to gather enough data to confirm either hypothesis. Meanwhile, continuing our journey through the central region of Andromeda, one can also notice one of the most enigmatic objects in this galaxy. The key feature of this celestial body is that it is almost impossible to see even with the most powerful optical telescope. However, everything changes if X-rays are used. In this part of the spectrum, this star is the brightest point in the galaxy. Observations show that the object is a binary system, one component of which is a low-mass neutron star. Its radius is only a few tens of kilometers, and it completes a full rotation around its axis in approximately 3 seconds. The second star in the system is a larger but relatively dim object, most likely a red giant. Calculations show that the total mass of both components does not exceed 3 solar masses, and the distance between them is very small. Every 4 hours, the neutron star is eclipsed by its stellar companion, causing its radiation power to drop sharply and then return to previous values. It is also highly probable that due to the small distance between the stars, the neutron star is gradually accreting its companion, thereby continuously increasing its mass. According to calculations, this process will continue for several tens of millions of years. Ultimately, the second star will be torn apart by tidal forces and transformed into a bright and hot annular nebula. Meanwhile, this astonishing object is just one of many stars densely surrounding Andromeda's nucleus. Together, they form a massive bulge about 12,000 light-years in diameter, with a noticeably elongated shape. M31 also has a prominent bar, but it is oriented edge-on to us and is virtually invisible from Earth. According to calculations, its length is around 17,000 light-years, and its width is about 600 light-years. In total, about 30% of Andromeda Galaxy's entire mass is concentrated in its central part. Gradually moving away, we can see that the edges of the bar form the basis for 2 gigantic spiral arms, majestically coiling around the galaxy's center. At the same time, between them are darker gaps, whose width is significantly greater than in the Milky Way, reaching 13,000 light-years. Calculations show that Andromeda's arms contain approximately 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, interstellar dust and gas concentrate in the arms, forming numerous star-forming regions. Over time, these gas and dust clouds transform into open clusters and associations, containing a great variety of young stars. Their light is reflected and scattered by cosmic nebulae, allowing the galactic disk to shimmer with fantastic polychromy. In one such cluster, an astonishing star named AE Andromedae is located. It is one of the brightest stars in the galaxy, and is a hot blue giant whose luminosity changes without any visible pattern. Such cosmic objects, called luminous blue variables, are extremely rare in the universe. To date, science knows only a few dozen such unique stars. Due to extremely high temperatures and colossal pressure, the outer layers of the star AE Andromedae are constantly in a state of unstable equilibrium, and the internal processes occurring within its interior are largely characterized by chaos and unpredictability. Periodically, powerful streams of superheated plasma collide with each other, causing dazzling flares capable of increasing the object's luminosity by several tens of times. There is a hypothesis that the most powerful of these phenomena could amplify the star's brightness by several million times. Such an event is called a pseudo-supernova and can occur at any moment. Measuring the parameters of such an unstable star, which is also at a great distance, is an extremely complex task. However, thanks to modern ultra-precise telescopes, it has been established that the mass of AE Andromedae ranges from 50 to 120 solar masses. Its radius at peak pulsation is approximately 55 times that of our Sun, which is only slightly less than the orbit of the planet Mercury. At the same time, the star's surface temperature reaches almost 20,000 Kelvin, and its brightness surpasses the Sun's in the range of 500,000 to 700,000 times. Like all blue giants, AE Andromedae continuously emits a powerful stellar wind, whose speed, according to calculations, can reach 100 kilometers per second. As a result, the object loses about 2 quadrillion tons of matter every second, which means an annual mass decrease comparable to 10 Earth-mass planets. However, for a star of such colossal size, this is practically imperceptible, since AE Andromedae will complete its evolutionary path significantly earlier than losses from stellar wind reach even 0.1% of its total mass. The reason lies in the fact that, despite its relatively young age by cosmic standards of 2 million years, AE Andromedae has already passed most of its life cycle. According to calculations, within the next million years, this star will explode as a supernova, leaving behind a black hole surrounded by a vast gas and dust nebula. Discussing the age of stars, it is necessary to note their uneven distribution throughout the galaxy. This allows us to look into Andromeda's past and trace the stages of its formation. The oldest stars, whose age is approximately 11 to 13 billion years, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms primarily contain younger stars, formed approximately 3 to 4 billion years ago. Here, in numerous stellar nurseries, are also very young stars, born only a few million years ago. This fact indicates that in the first stage of its evolution, the M31 galaxy was significantly smaller in size, and its shape resembled an ellipse. Furthermore, by analyzing the parameters of individual stars in Andromeda, one can define such an important yet rather conditional concept as the galactic habitable zone. It is believed that the high concentration of stars in Andromeda's central part, as well as increased radiation levels and unstable orbits of potential exoplanets, make this zone unfavorable for the emergence of life. At the same time, distant planetary systems located on the galaxy's periphery are too poor in heavy elements, leading to a deficiency of rocky planets similar to Earth. Consequently, only the intermediate region of the galaxy can be considered hypothetically habitable. It is in such a zone, at a distance of several tens of thousands of light-years from the galactic center, that a small, dim object known as Megam ML7 is located. It is a red giant whose mass is relatively small, approximately 50% of the Sun's. In 1999, thanks to a fortunate coincidence, astronomers managed to observe a microlensing event, during which they were able to study this inconspicuous and distant cosmic body in more detail. As a result of the measurements, the star's mass and spectrum, as well as its surface temperature, which was approximately 3,700 Kelvin, were determined. But the most important observation was the rhythmic deviations of the star's trajectory from its main direction of motion. Such oscillations are considered a sign of the possible presence of a sufficiently massive companion to the star. The presumed object was named Megam ML7b and is currently considered a potential exoplanet. If the existence of this celestial body is confirmed, it will enter the annals of astronomy as the first exoplanet discovered outside our home galaxy, the Milky Way. Information about this mysterious object is still scarce, but preliminary calculations indicate a high probability that it is a gas giant whose mass is approximately 6.3 times that of Jupiter. There is also evidence that in terms of the richness and diversity of chemical elements, this stellar system is most likely not inferior to our own, which means that within its bounds there are very high chances of encountering various types of planets. Not only colossal gas giants, but also solid rocky celestial bodies similar to Earth. Upon a more detailed study of the Andromeda galaxy, the observer's eye is met with another astonishing feature: an abundance of star clusters and associations, whose number significantly exceeds that in the Milky Way. In total, M31, as it is also called, is known to contain about 460 globular star clusters and approximately 10,000 open clusters, as well as several dozen massive stellar associations. Some of them are concentrated in the very heart of the galaxy, others are chaotically scattered in its halo, while still others are firmly established directly in its majestic spiral arms. One of the most grandiose and noticeable structures is the cluster NGC 206, located almost at the very edge of the galactic disk. In the past, this aggregation was considered a globular cluster, but currently, due to its colossal size, it has received a higher status and is now referred to as a stellar association. In this region of cosmic space, with a radius of approximately 200 light-years, about 300 extremely bright stars and countless less noticeable stars are concentrated, whose total mass reaches approximately 200,000 solar masses. Their combined luminosity is so great that the association is visible from Earth even with an amateur telescope, on par with the galaxy's nucleus and arms. According to observations, NGC 206 arose from the merger of at least two large gas and dust nebulae, separated by a dark lane of interstellar dust. One of them is about 10 million years old, while the other is noticeably older, having formed about 50 million years ago. The single giant nebula became a powerful point of gravitational attraction for the surrounding interstellar gas, which led to the formation of a grand star-forming region. Over time, some of its constituent stars will disperse into the surrounding space, while others will form a large globular cluster. The galactic disk of M31 contains many such formations, and not all of them initially formed within its boundaries. It is hypothesized that many large stellar associations are nothing more than remnants of great cosmic catastrophes of the past. According to calculations, over its entire existence, Andromeda has absorbed more than 100 satellite galaxies. Some of them dissolved without a trace, while others transformed into gigantic stellar streams. The most grandiose event, however, can be considered the collision with an object known to us by the index M32. This compact elliptical galaxy is located above Andromeda's disk, only 17,000 light-years away from it. Its diameter is about 8,000 light-years, and for such a small size, this galaxy has a fairly high mass, around 1 billion solar masses. At the center of M32, there is a supermassive black hole, approximately 2.5 million times heavier than our star, which is surprising for such a compact object. In fact, M32 is merely the remnant of a much larger galaxy that survived a grand cosmic catastrophe. Data obtained from the Spitzer Space Telescope indicate that about 800 million years ago, a large satellite galaxy at immense speed punched through Andromeda's disk, leaving a significant hole in one of its spiral arms. During this collision, M32 lost most of its stars, and restoring its former appearance is unlikely. It is hypothesized that it could have been a full-fledged elliptical galaxy or a small spiral, of which only the central part remained. Besides M32, Andromeda has about 30 satellite galaxies, connected to it by invisible threads of gravity. The brightest and largest of these is M110, whose diameter is about 15,000 light-years. Most of the others are dwarf spheroidal galaxies and are located within 1 million light-years. Nevertheless, altogether they form the Andromeda subgroup, which in turn is part of the local group. Its other members include the Milky Way and its surroundings, as well as the Triangulum galaxy and some other objects. The relentless forces of gravity are gradually pulling the local group towards a common center, which is why the Andromeda galaxy is rapidly moving in our direction, covering over 300 kilometers every second. From the perspective of the scale and grandeur of cosmic space, our home planet is merely a small rocky fragment hurtling at incredible speed through the boundless expanse of emptiness. For billions of years, it has tirelessly traversed its orbit, maintaining a constant distance of approximately 150 million kilometers from the Sun. However, the true dimensions of our star system significantly exceed these figures. According to current scientific understanding, its outer boundary, which is considered the far reaches of the hypothetical Oort cloud, extends to a distance of about 100,000 astronomical units. Beyond this imaginary limit begins the boundless abyss of interstellar vacuum, a space so rarefied that, on average, there is only a single hydrogen atom per cubic centimeter. The distance between the nearest stars in our region of the galaxy is measured in several light-years. And a photon that left the Sun can reach Proxima Centauri without ever colliding with any particle of matter. This boundless emptiness is an all-encompassing and integral component of the deep structure of the cosmos. It permeates the entire Milky Way like an insurmountable chasm separating stars and planets, black holes and white dwarfs, superdense pulsars and diffuse nebulae. If we mentally move beyond the limits of our galaxy, we can find that it is surrounded by an even deeper and more extensive vacuum. For example, between us and the Andromeda Galaxy stretches 2.5 million light-years of ultra-rarefied space. This distance is so colossal that 25 galaxies like our own could easily fit within it. However, it is filled only by the deepest cosmic vacuum, and this is just a small fraction of the great cosmic abyss. The pervasive, invisible threads of gravity bind together the Milky Way, the Andromeda Nebula, and the Triangulum Galaxy, as well as about 100 of their satellites. This structure is called the local group, and represents a large cluster of cosmic matter whose diameter is approximately 10 million light-years. In turn, the local group is part of an even larger formation, a relatively small galactic filament by universe standards, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years and a thickness of about 5 million light-years. The sheet, in turn, is part of an even larger aggregation called the Virgo supercluster. However, very close to the local sheet, cosmic space suddenly changes its usual appearance. Here, the familiar polychromy of the universe is disrupted by the appearance of a gigantic black void, known as the local void. In fact, the local sheet forms one of its walls. Other hypothetical boundaries are the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into hypothetical parts by several rarefied galactic filaments, and wide passages connect it into a single network with the adjacent Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of surrounding matter, the volume of the local void slowly but steadily increases. Currently, its diameter is approximately 150 million light-years, and the distance to its center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic emptiness is located quite close to Earth, at a distance of about 3.2 million light-years. Thanks to this proximity, the local void occupies a significant portion of our planet's night sky, about 40%. The main plane of the Milky Way, containing many bright stars and large nebulae, obscures the central part of this region from us. However, its edges remain accessible for observation. In 1854, slightly north of the constellation Hercules, a dwarf spiral galaxy named NGC 6503 was discovered. Later, with the development of observational techniques, it became known that it is located in the middle of the local void, and its distinctive feature is its incredible polychromatic appearance. The galaxy's spiral arms are permeated by bright red clumps of heated hydrogen, and shimmering blue nebulae are sites of starbirth. The center, meanwhile, is darkened by clouds of cool gas and dust, having a noble brown color. The diameter of NGC 6503 is approximately 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the powerful gravitational influence of the Virgo supercluster, this galaxy is continuously approaching our planet at a speed of about 43 kilometers per second. Specialists suggest that the gradual approach to the local sheet will eventually lead to the saturation of its cosmic space with interstellar hydrogen, which will serve as a catalyst for intense star formation. According to calculations, after several billion years, the number of young stars could double from the current figure, and this small galaxy will shine with new, astonishing power. The movement of NGC 6503 provides a vivid and convincing illustration of how voids, gigantic cosmic emptinesses, most likely formed. There is a theory that the fundamental foundations of the large-scale structure of the universe were laid in its earliest stages, during periods of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power then shook the young universe, giving rise to local condensations and vast voids. Subsequently, these clumps of matter transformed into protogalactic clouds, and regions of reduced density became what we now call voids. Over time, the all-encompassing influence of gravity only amplified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space within voids even more rarefied and empty. Observations conducted by modern astronomers show that the vast majority of galaxies formed between 10 and 13 billion years ago. Notably, no significant differences were observed in the age of galaxies located in cosmic voids and those that form global cosmic filaments. This fact serves as additional confirmation of the modern theory of the formation of the universe's large-scale structure, emphasizing its consistency with empirical data. Meanwhile, if we consider the phenomenon of cosmological expansion of space, it can be assumed with a high degree of probability that over time, the local void will continue to increase in size and become even more rarefied. Simultaneously, the Virgo supercluster, which we observe today, will gradually break down into several independent groups of galaxies. Currently, however, it is a colossal aggregation consisting of approximately 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. The total mass of this cluster is about 1.5 quadrillion solar masses, which is equivalent to approximately 1,000 galaxies like our own Milky Way. The Virgo supercluster partially touches two other gigantic galactic superclusters, the Centaurus supercluster and the Pavo-Indus supercluster. At the same time, another side of it borders a vast region that is almost completely devoid of visible matter. This region is called the Taurus void and is one of the largest known cosmic voids discovered to date. Studying this area of cosmic space presents great difficulties for astronomers. The complexity lies in the fact that a significant part of the Taurus void is located in the so-called zone of avoidance, a sector that is obscured from our view by the plane of the Milky Way. Bright stars of our own galaxy outshine weaker and more distant light sources, and interstellar matter actively absorbs and scatters their radiation. However, thanks to advanced research conducted in the infrared range, we have still been able to gain some understanding of the internal structure of this void. The diameter of this grand cosmic emptiness is approximately 200 million light-years, and the distance to its center is about 150 million light-years. When observing the void, one is immediately struck by a surprisingly clear and sharp boundary between the relatively empty space and the bright, dense cluster of galaxies located noticeably further away. This cluster is called the Perseus-Pisces supercluster and is one of the largest and most significant in this part of the universe. Such a sharp and distinct transition is usually characteristic of field clouds, but infrared studies conducted in this region do not confirm their presence. In all likelihood, the clear boundary between the void and the supercluster is due to complex gravitational reasons, but the exact mechanism of their action we have yet to discover and fully understand. Meanwhile, it is assumed that the Taurus void, like most other cosmic voids, is not as empty as one might imagine at first glance. Distortions of light passing through it allow scientists to suggest that this region may conceal giant gas and dust clouds in its depths, potential cradles for future galaxies. According to other, no less intriguing hypotheses, huge masses of dark matter, the most enigmatic substance in the universe, whose properties are still not fully understood and remain the subject of active scientific research, may be hidden within the void. Among the boldest ideas put forward to explain the nature of cosmic voids are assumptions about the presence of clumps of antimatter or even more exotic forms of matter with negative mass in their centers. However, despite their boldness, these hypotheses fall outside the scope of generally accepted scientific concepts, which makes their experimental verification extremely difficult. To date, astronomers have discovered only 2 isolated galaxies lost in the boundless space of the gigantic void. One of them, known as UGC 2627, has a spiral structure and outwardly resembles our Milky Way. The second, named UGC 2629, belongs to the category of elliptical dwarf galaxies. Both of these cosmic objects are located almost in the very heart of the void, at a distance of approximately 185 million light-years from Earth. Notably, the distance between them is relatively small, only a few 100,000 light-years. It is quite possible that other solitary galaxies are hidden in this vast empty space, but the disk of the Milky Way prevents their detection from our side. Meanwhile, the Virgo supercluster, in alliance with 4 other superclusters, forms a colossal galactic filament called Laniakea. This grand structure contains over 100,000 galaxies and stretches across cosmic space for a distance exceeding 500 million light-years. Its gravitational center is the Great Attractor, an enigmatic supercluster of galaxies located 250 million light-years from our planet. In turn, Laniakea is a component of a vast galactic flow. If we move even further away, we can observe that most of it is surrounded by a black abyss of unimaginable proportions. In this cosmic void, the light of distant galaxies dissolves, and even mysterious, almost elusive neutrinos require billions of years to traverse this cosmic chasm. Astonishingly, despite all the achievements in observational technology, such a gigantic void was only noticed 10 years ago. This occurred in 2013 at the University of Wisconsin-Madison. A team of astronomers, led by Professor Amy Barger, was engaged in determining the distances to galaxies. During this research, an unexpected and stunning fact was discovered. It turned out that Laniakea, as well as a significant portion of the superclusters adjacent to it, are surrounded by a cosmic void of unprecedented scale. After meticulous calculations, scientists established that its diameter significantly exceeds the size of any previously known void. The scale of the discovered void was so enormous that it cast doubt on several fundamental cosmological principles. Evidently, the universe turned out to be much more complex than we had imagined. The research by Amy Barger, Ryan Keenan, and Lennox Cowie led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work convincingly demonstrated that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC after the first letters of its discoverers' names. Observations show that the shape of this gigantic void is close to spherical, and its diameter can exceed 2 billion light-years. According to calculations, the Milky Way is located several hundred million light-years from the hypothetical center of the Great Cosmic Abyss and approximately the same distance from its edge. The discovery of the giant bubble of emptiness surrounding Laniakea helped explain a paradox that had troubled scientists for many years. The fact is that all galaxies in the universe are gradually moving apart due to cosmological expansion. Measuring the speed of this movement allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of space expansion. However, if we use the nearest galaxies to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. Conversely, if we use distant objects as a basis, the Milky Way's surroundings move faster than they should. The discovery of the void put everything in its place. The fact is that galaxies within it, including the Milky Way and its neighbors, constantly experience additional gravitational influence from objects located outside the void. It is this influence that creates the additional force that gradually stretches our cluster in different directions. It is astonishing that the KBC void has such a colossal extent that it contains not only vast superclusters of galaxies, but also other cosmic voids within its depths. For example, the local void, as well as the torus void, are integral components of its grandiose structure. It follows that, in comparison with other voids, KBC, although it appears colossal, is by no means as uninhabited. Nevertheless, against the backdrop of the observable part of the universe, whose diameter, according to calculations, reaches 92 billion light-years, Even it appears as merely a barely discernible dark speck. If we turn to the global map of the universe, we can find countless dark regions comparable in scale to the KBC void. Most of them easily fit within the framework of modern physical concepts. Others, however, exhibit astonishing and unusual characteristics that are difficult to comprehend scientifically. One of the most outstanding cosmic puzzles is the Eridanus supervoid, also known as the relict cold spot. According to calculations, its diameter ranges from 500 million to 1 billion light-years, and its distance from the Milky Way is between 6 and 10 billion light-years. This indicates that this formation is one of the most extensive elements of the universe's large-scale structure. This void is located in the southern hemisphere of Earth's sky and occupies a significant area, several times larger than the size of the full moon. However, it is completely impossible to see it with the naked eye. The relic spot becomes discernible exclusively with specialized telescopes that observe the cosmos in the microwave range. Thanks to these instruments, astronomers have established that within the spot, the universe's cosmic microwave background radiation is approximately 70 microkelvins colder than the average across the metagalaxy. This deviation is almost 4 times greater than the most significant anomaly previously recorded, and its gigantic size makes it a truly enigmatic object, requiring comprehensive study. Currently, it is believed that cosmic microwave background radiation, traversing hundreds of millions of light-years of deep vacuum, is subject to gravitational influence from distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose some of its energy, as a result of which the relict spot appears colder in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of the cosmic microwave background radiation. According to calculations, the gravitational pull of external galaxies can only account for 1/4 of the observed deviation. It is hypothesized that the remaining 75% of the effect could be the result of the influence of hypothetical dark matter or dark energy concentrated in the depths of the void. However, truly unraveling this cosmic mystery is still a very long way off. Some cosmic formations are so grand that their scales are difficult for human comprehension. These colossal structures play a decisive role in shaping the universe, and therefore their study can provide us with the key to understanding its past and future. Every atom of our world is integrated into the giant mechanism of all-consuming cosmic space. Its study may take many generations, but ultimately it will allow us to find our place in the infinite universe.